All right, let's resume our discussion. We are going to work on two topics today. First thing we need to do is to wrap up the network flow, and our goal is to design an algorithm that's running in polynomial time that solves the network flow problem. So the high-level idea is to tweak the existing focus on algorithm, and then we are going to move to our last topic, the intractability. So now let's get ourselves started to work on the first item, the network flow. So last time we were talking about one very bad cases in which if we are not careful in designing the network flow algorithm, then we are going to end up with very slow running time solution, although that eventually will give us a correct solution. So let's look into the instance we were talking about. So we were talking about an instance in which there are only four nodes, S, T, A, B, and for all the four edges, their capacities are going to be 100. So these four major edges have a capacity 100, and there's one extra like special edge whose capacity is only 1, right? So these are all the capacities, right? So we were saying that if we run the Fulkerson algorithm on this instance, and we really just don't impose any restrictions on how we choose the augmenting path, then the running time will be very slow, right? So the execution, the bad execution looks as that, right? So we start with the original graph, and we do want to start with finding an augmenting path, right? So that basically we want to find a path that connects between S and T that allows us to push more flows, right? So in the beginning, the flow is really just empty, right? So everything is 0, right? So this is the flow graph, and this is the original input graph, right? So we start with 0, and then we do want to first find an augmenting path, right? So in case we find an augmenting path that looks like that, right, the one highlighting in black, then we are going to push 1 unit of flow along this path, right? So now we do an update, and after we push 1 unit of flow, then the residual graph get updated as well, right? So this is what the new residual graph looks like, right? So this is 99, this is 99, this is 100, these two are 100, right? The only difference is this edge, the edge over here, right? So originally the AB edge is connecting from A to B, and after we use this edge in our first update, the direction of the edge get flipped, right? So it's now moving from B to A, right? So in the second round, we can continue to find another augmenting path. So in case we find the augmenting path that looks like that, right? So then our flow get updated, right? So after we update both flows, right, eventually we will get something looks like that, right? So 1 unit of flow from the first round, second unit of flow from the second round. When we merge something in the middle, the flow that's crossing between A and B get canceled out, so we don't need to consider about that, right? So this would be the solutions we have so far, right? So again, just the right hand side is the solution we have, the left hand side is the residual graph, right? After we do that, right, if we continue to update the residual graph, right, so we sort of see a repetitive patterns here, right? So after we do 2 rounds of update, all the capacity would be 99. The edges that's connecting between A and B get flipped again, right? It's from B to A back to A to B, right? So this would be the new residual graph, right? So in case we keep doing the same thing, we will find another augmenting path, and then we sort of do another update, right? So now this time, this is what we get: 2 1 2 1 1 0 0 0. Right, so this is STAB, right? So this would be after we find this augmenting path, we integrate this path, the new flow with the existing flow, and then we will get a new flow, right? So if you keep doing that, right, so you will just see that what's going to happen is that you see this kind of residual graph, and what's going to happen is that the number here, right, it's going to gradually decrease, right? So this is gradually decrease, right? Gradually decrease, right? It's you can sort of see that it's moving from 100, right? Originally it's 100 to 99, and then after this 99, then it becomes 98, right? So and then it becomes 97, all the way slowly you will go down to 0, right? This is going to be true for all these 4 edges, right? So all these 4 edges are going to gradually decrease, right? So they are going to have very slow decrease rate. And for the rest of the edge over here, it's going to just flick back and forth, right? So eventually what's going to happen is that after around 100 steps, eventually we will be able to find an optimum solution that's having 100 from one side and 100 from the other side, right? So this is the optimal solution, right? I think we need 200 steps instead of 100. It's 100 times 2, right? So eventually we will be able to find a solution, but it's going to take us 200 steps, right? So basically, in general, the number of steps here, it's really just going to be the same as the capacity of the S20a, right? So it's going to be this. If I somehow like get another graph so that the capacity here is 1,000, 1,000, 1,000, and 1,000, and this is also 1, then this number is changed from 200 to 2,000, right? So basically it's the solution is very sensitive to the largest capacity, right? So let's really just recall that if the number of rounds is linear in the maximum capacity, then this is not a polynomial time, right? So let me write this down. If number of rounds is poly in the capacity, then it is not a polynomial time. So the reason is that in order to describe the capacity, right? So because the description capacity is going to not be linear in the description complexity of the capacity is not linear in C cap. It's log in cap, right? So in the sense that if I want to describe a number, say that a number 1,000, the number of bits I need would only be log 1,000, right? So basically this is really just saying that in order to describe this kind of instance, right? So we only need much smaller number of bits compared to 1,000. Right. So in other words, if we have to use a 1,000 round, then this is not polynomial time, right? This is the setup of this problem, and our goal is to really just be able to fix this problem. So now let's switch back to the slide, and then now we are going to work on an algorithm that fixes the problem, right? So just recall the kind of problem we are facing, right? So if we have a residual graph that looks like that, say this is 95, 195, 95, 95, right? So it's really just in the middle of the execution, right? So the only problem that exists in the fault-focusing algorithm is that we let the algorithm to choose an arbitrary augmenting path, right? It's really just any path that allows us to move from S to T. I will just choose that and update that, right? So we have been a bit careless in choosing the augmenting path, right? So the very high level idea is that can we fix that? Can we be a bit smarter to choose not choose this very sort of stupid, silly augmenting path, right? So the easiest to fix, right, intuitively, is that when you block, you just pretend this edge doesn't exist, right? So we sort of pretend this doesn't exist, not exist, right? Then basically we will have a residual graph that looks like that, the 95, 95, 95, 95, right? So once we pretend this doesn't exist, then all of a sudden the only the only augmenting path we can choose is one of these two, right? Choosing either one of these two will really just help us to speed up our algorithm a lot, because we are not going to face these silly things to really just have to increment our flow by 1 unit at every run, right? So we can increment 95 units at one round, right? So this would really just be the intuition, right? So the moral of the message here is that sometimes, right, although it's true that when you have more pipelines, it's always going to help you a little bit in terms of finding the optimal solution. But when we look into the augmenting path, sometimes removing some edges, right, pretending the edges doesn't exist or try to avoid those small capacity edges will help us to find the augmenting paths that are in better shape, right? So in general, our goal is to use care when selecting an augmenting path, right? So the model here, like we have been looking into two instances, right? The first instance is that sometimes if we are extremely careless, then we can come up with a solution that's running in exponential time. Exponential just means that the number of runs will be linear in the capacity. And sometimes we say that, well, at least for this specific instance, trying to fixing the problem is quite straightforward. We can just pretend that one of the small edges doesn't exist for a moment, and then all of a sudden we are able to find very good paths, right? So the moral here is really just that if we are trying to be clever, then clever choices of the augmenting paths can lead to polynomial time algorithms, right? So there's one thing we need to pay attention to before we proceed. Like this is not, we are not going to spend excessive effort to tackle this special cases, but you just need to keep that in mind. So it's really just that when the edge capacities can be irrational, then there's no guarantee that the fault focusing algorithm terminates or converge to a maximum flow, right? So basically, say for instance, if you have this kind of graph, right? So this is square root of 2, 100. This is 100 square root of 2. Like for instance, this pi. This is 100 square root of 3, right? 100 square root of 3, right? So now in this case, when you handle the bottleneck, right? So the bottleneck is over here, right? So every time you're really just trying to update the flow, using by a irrational number, right? So in this specific case, we need to update the flow by pi unit, right? Pi is the 3.14, those kind of irrational number you learned for that's related to circles, right? So now when we do this kind of update, why there's an intuition that we're going to get into trouble? This is because that let's just recap that the reason we believe this algorithm works, right? So the reason we believe this algorithm works is that you pick up any flow, you pick up any network, right? So there's an upper bound, right? Upper bound on the maximum possible flow, right? So that say that after I did some very crude calculation, I know that the maximum flow cannot be 10,000, right? There's an upper bound, and there's also a minimum increment, right? So we were sort of assuming that all the edge capacity is an integer, right? So if all the edge capacities are integer, then the minimum increment will be at least 1, right? So if every time you increment the flow by at least 1 unit, and eventually there's an upper bound, right? Every time there's at least one unit of increment, eventually there's an upper bound. That means that you need to use only constant amount of runs, right? Finite amount of runs in order before you have to stop. Right, but this argument sort of falls apart if your increment can be an irrational number, can be some number that's very very small, right? So if there's if there's a number that looks like square root of 2 minus 2 something minus 1.4, right? So if you have this kind of numbers, then the argument we have been using fails to work, right? So you will be able to come up with a flow that's monotonically increasing, but we will still be able to have an upper bound, right? Have a crude upper bound on the maximum capacity. But that really just says that this monotonically increasing, it will sort of converge to some number, right? So if you look into your real analysis, if you have a sequence of number that's monotonically increasing and bounded above, eventually it will converge. But it doesn't say that it will converge to the right number, right? So basically, there we can, like, if with some careful constructions, we will be able to see that there are some cases for which the edge capacity are irrational number, the algorithm never stops, or even it never stops sometimes. Even it never stops, there could also be a chance that there could be chances that it never stops but it converges to the right number, but it's even worse than that, right? So sometimes it even converges to the wrong number, right? So let me just articulate this a little bit, to make it clear, because it gets into a bit of the details of the convergence property. let me just switch back to the notes, the white. Right. So now we sort of face three words, right? The first word is that all the capacity are integers. In this case, we sort of know that there's an upper bound, right? So you sort of have a crude estimate of the upper bound of the network flow, and then every round, your flow increment by at least 1 unit, increment by at least 1 unit, right? In this case, then you sort of know that the termination will be nation. The number of rounds will really just be at most, right? So let's call this upper bound to be L, will be at most L, right? This is the first word, right? In the second word, right? So we saw if we just look at the sequence of the flow, right? The sequence of the flow we construct, right? This will be monotonically increasing. And we also sort of have an upper bound on this sequence, right? So if you look at the real analysis, if a sequence is monotonically increasing and the sequence has an upper bound, that sort of implies this sequence converge, right? So converge. Right, so let me just write that down, unfold the mathematical statement. So let's say that f1, f2, fn, be a sequence of flow value. In case if fi is increasing, monotonically increasing, and fi is always less than a constant, then we know that the limit, right? The limit of fi converges to a specific number, right? We don't know the number, but we know it converges, right? So there are two implications here, right? So the first implication is that maybe there's a case one, right? There's the first possibility is the converged value would really be the value of the optimal, right? It's really just the same as the optimal, right? This is the first possible case. In this first possible case, what we are going to see is that there's an optimal solution. We are going to have a flow. We are going to build a flow that are gradually getting closer to this optimum solution, but it does not say you will hit this number, hit the optimum solution with a finite round, right? So it could be possible that the optimum solution is 1. In the first round you get 0.9, the second round you get 0.99, and third round you get 0.999, and you can keep doing the same thing, like keep going, like have a lot of nines, but it never hits 1. But it gets closer and closer to 1, right? This is actually one of the more benign case, because you sort of know that you are, even though you don't exactly hit the optimal, you are getting closer to the optimal, right? There's a second case, actually, the slides is saying that it's actually, if we construct things carefully, there's a second case that says that although, right, there's a limit, right, eventually it will converge, right? It will converge to a certain number, right? So this is really just the result from real analysis, right? It's really just a fundamental property. If your sequence is monotonically increasing as bounded above, you will eventually converge, right? So no matter what, that's sort of even independent of the algorithm, right? But there's a possibility that convergence point is actually different from the value of f, right? So it could be that we haven't ruled out the possibility that the optimum solution looks like here, right? This is the value of the optimum solution. But when you run the Fokker-Folkestone algorithm, it sort of converges to a different number, different value, right? So it sort of like hits to, so there's a ceiling here, right? So because we only know there's a ceiling, right? Because we only use some basic result of real analysis, right? So the ceiling is C0, but it's possible C0 is still smaller than value of f, right? Right. So both cases are pretty nasty, because both cases says that it's hopeless to wait for the algorithm to terminate. But there could be even more nasty case where just that even the convergence points is different from the optimum point, right? So this is the implication when the network could have irrational capacity. But on the other hand, when it's in a lot of practical problems, right, we rarely faces instances that have irrational capacity. So here, what I have been talking is really just that you need to be aware that things can go very funny and very strange when you allow irrational number. But at the same time, for the purpose of this course, we shouldn't think too much about the irrational numbers, right? So from here on, right, we should just completely forget, right? We will just assume that all the capacities are integer. Even like as we have shown that even all the capacities are integer, we could still get into trouble, right? We only know that it will eventually terminate, but for some bad cases, the termination time is going to be very, very long, right? So what we are going to focus on next is that we are just going to focus on tackling these kind of bad instances, right? So we are not going to tackle those very nasty instances where the irrational numbers are even allowed, right? Let me just switch back to this. Right. So basically, there was a detour that's talking about this particular statement. It's innocently simple, right? So when edges capacity can be irrational, no guarantee that fault focuson terminates or converge to a maximum value flow, right? So the statement itself could be innocently simple, but right, that when we unfold the meaning, right, that was we sort of have to spend a few minutes to talk about that. Right. So let's head back to our major objective, right? So we sort of want to be able to choose an augmenting path, such that we can substantially reduce the number of iterations and avoid those back augmenting passes, right? So now there are quite a number of possible approaches to choose the augmenting passes, right? So the first intuitive one is that it's really that when it's really just inspired by the bad instance we were talking about, right? So if we have this kind of graph, right? So ideally, the best augmenting path would be the augmenting path that has the maximum bottleneck, right? So basically, we want to find a path, right, such that we want to maximize the minimum of the capacity in the path, right? So among all passes, both passes, right? So there could be multiple passes that are moving from S to T, right? So for each of the paths, right? So let's say this is P1, this is P2, and then this is P3, right? There could be exponential number of passes, right? And in order to so for each of the paths, right? So we can uniquely find the bottleneck, right? There's always one edge that has the smallest capacity, right? So when we look into the residue graph, right? So this is the bottleneck, right? So one very natural idea is to find the path such that it's bottleneck, right? So let's call this is bottleneck. It's maximized, right? So if we were able to find that, then basically we are guaranteed to always find the best and highest quality augmenting path in every single round. And when we do that in this particular instance, then we will choose the augmenting path that's really much more friendly than the one we were choosing, right? You will eventually choose this augmenting path so that its bottleneck is 100 instead of 1, right? So if we choose this one, the one that's going through the middle edge, right, then basically the bottleneck would be much smaller, right? So that would be one possible idea, to choose the path with the highest bottleneck, but or the fattest bottleneck, right? So but the main problem here is that it's actually very difficult to choose such a path, right? So just recall that the number of possible paths that are connecting between S and T could be exponentially large, right? So among the exponential number of paths, in order to choose one that's the highest quality, itself seems to be a very challenging problem, right? So there's a question mark here, right? So what we are going to do is we're going to try to mimic this idea of choosing the higher quality augmenting passes, right? Measured in terms of the bottleneck, but we cannot exactly choose the fattest one, right? So this is the second approach. We are going to choose sufficiently large bottleneck capacity, right? There could also be other possible approaches which we are not going to cover in the lecture, right? So there could also be an approach that chooses the fewest edges, right? So if we choose this policy, then it turns out that we can also argue that the algorithm terminates in polynomial time. But for the purpose of this lecture, right? So we only focus on the second approach. We choose a sufficiently large bottleneck capacity, right? So we cannot do the first approach because finding the best augmenting path itself is going to be very difficult, and we are just not going to talk about the third approach. This is first, this is second, and this is third approach, right? So now, our second approach, we call this algorithm capacity scaling algorithm, right? So the high level idea, let me just read out the text carefully, right? So we just need to choose augmenting paths with large bottleneck capacity, right? So the high level idea is that we sort of want to maintain a scaling parameter here, right? The parameter is delta. This delta starts to be a pretty large number, and what we need to do is really to just at some point we just want to when we are in the middle of the process, we just want to eliminate all the edges whose capacities are smaller than delta, right? So this is what the second sentence is talking about. Let the GF of a delta be part of the residual network that contains only edges with capacity that's at least the delta, right? So here is a working example here, right? So if we do have a graph that looks like the graph on the left hand side, right? So again, we have a very troublemaker, right? There's an edge that's connecting from between A and B, and then whose capacity is only one. The rest of them have very large capacities, right? So in case we let our delta to be 100, then what's going to happen is that we are going to delete all nodes, all edges whose capacity is less than 100. Right, so now we just examine all these 5 edges, right? So there's only one edge whose capacity is less than 100, right? So we just delete that. So we will come up with a subgraph of the original one, right? So the relationship between these two graphs is that after the deletion, of course, like the new graph is a subgraph, of the original one, right? So this is what we are going to do. After we do the deletion, then we find the maximum capacity edges, right? So maximum capacity. After we do the deletion, what we need to do is that okay, it's not working. I need to stop and then restart a bit.